All right, great. Thanks so much for the introduction and for inviting me. Today, I'm going to talk about my work on sequential motifs in observed walks. This is work I did during my PhD at Northeastern with my collaborator, Ingo Schultes, who's a professor at the University of Würzburg in Germany, and my PhD supervisor at Northeastern, Tina Aliasirad. So I don't think I need to do too much motivation about motifs in networks to this seminar, but to start with, motifs are small substructures that characterize complex networks, and they've been studied for a long time. This paper that I'm showing here is kind of some seminal work by Milo et al. From 2002, where they looked at motifs in what I'll refer to as static networks. So what we typically can think of as networks, where nodes are nodes and there are connections between them. You'll see why I'm making that distinction later. And they looked at these motifs in transcription networks, in neuronal networks, in neuroscience, and in ecological networks. And they called motifs the building blocks of complex networks. And so this has been a long studied area for the last 20 years. I guess we're coming up on the anniversary. And more recently, motifs have been moved to temporal and dynamic networks. So here I'm showing some paper on motifs in temporal networks that came out in 2017. As well as dynamic networks, where we might have snapshots of networks over time, and we compare the different motif structures that we see in the snapshots, and as well as dynamics on networks, so understanding how motifs relate to dynamics, and we'll talk a little bit more about that a little bit later. But network data also comes in the form of observed walks, otherwise known as pathway data or sequential data on networks. And this data has different characteristics, and it requires some specific methodology. And so as a motivating example for this kind of data, we'll think about flights. So people, passengers moving through a network of airports. So given some flight itinerary data, where each itinerary is a sequence of airports visited by passengers. So here we have 3 itineraries that we'll use as kind of a running example. One from Boston to JFK to Chicago, and then back to JFK. Another from Atlanta to Chicago to JFK, and then to Boston, and so on. Given a data set like this, our high-level goal is going to be to characterize the airport network based on the frequency and the significance of substructures that we find in this itinerary data. So those substructures being motifs. So let's think through a couple of potential solutions. Since I said people have been studying this for 20 years, we should probably think about what they've already done. So one option is to take this data that comes in the form of these sequences and collapse it into a static network, so a weighted and directed network, like I have here in the lower corner. And then we can count motifs from this static network. And we have, again, lots of different methods for doing this, some that take weights into account, some that don't, all sorts of options for how we can count motifs from static networks. But I'm going to argue that might not be a good idea for this kind of data. And the way I'm going to introduce the problem is to look at this directed cycle over 3 edges between JFK, Atlanta, and Chicago. So this one down here in the corner that I've highlighted in orange. And we can ask the question, does this cycle actually exist in the data that we have? So did any passengers actually follow this cycle? Because any static motif counting algorithm, or just computing the clustering coefficient, for example, of the network, is going to include this triangle as a relevant substructure, but we have more fine-grained data that can tell us whether anybody's actually using this substructure. And in this example, so now I've highlighted the same edges that are in this triangle, but in the input data, and we never actually see any passengers using the full cycle. And so it's a question about what we're trying to study, of whether we want to count this triangle or this directed cycle as a relevant motif for our analysis. So we see this cycle never actually happened. And there's a further problem, which is about the edge weights. So now I've collapsed this input data into a weighted network, and I have on the edges, the 2 edges with weight 2 and 1 with weight 1. And so if I want to understand how to understand the importance of this triangle in the context of the weights, it's really not clear. Should I take an average? Should I take a maximum? Should I have some other function? There's not a nice way, because the sequence of edges doesn't actually appear in the data, to count what this triangle means in the context of the weighted network. So probably counting static motifs is not a good idea. And we'll see later that specifically in data like this, it is a problem. So something to look forward to. Another solution we might try is using methods for temporal or dynamic network data. So we have lots of methods, again, to do this kind of thing. There's lots of methods for temporal network data and for dynamic network data to understand motif structures. But these types of data are completely different. Their unit of observation is very different from what we're looking at. So in the temporal network data, we're typically given time-stamped edges. And so each observation of an edge is independent from any of the other observations. But in the observed walks, we're looking at sequences of edges that were observed together typically without any time information. So we don't know what time this edge happened and what time the next edge happened. We just know that there was this edge, then there was that edge, and that's one unit of observation. Similarly, with dynamic network data, it doesn't map on very nicely. So here we might have snapshots of a graph at discrete times. So then edges can kind of come in and out of the system over time. So there's this notion of edge deletion, which doesn't make sense in the walk data that we're looking at. And again, there's usually some kind of time scale associated and some kind of synchronization that you can either infer or that you know across the different snapshots that you're seeing. But we don't have any of that. So for example, I can't say just because the first airport is Boston, Atlanta, and Boston for these three different itineraries, I don't know that those trips all started at the same time. I don't know whether there was a long layover later in the trip that made the timescales different. I just don't have that information. And so it doesn't really fit with dynamic networks either. And finally, there's a more recent idea from Schwartz and Porter called process motifs. And in this case, they took structure motifs and looked at how those structure motifs relate to a macroscopic process happening, a dynamical process happening on top of the network. And then they related the structural motifs in the graph to the dynamical motifs that they called process motifs. But in our case, we're really just interested in structural motifs. So we're not taking that extra step. But I point this out just because we're starting from the output of a discrete dynamical process, basically a random walk on a network. And so there are connections between their work and ours, but it's not exactly what we're trying to find in this work. So we have three solutions that didn't really work, and we don't have a solution that's directly applicable, so we're going to come up with one. So today we're going to talk about counting and analyzing motifs using higher order networks. So to do that, I need to tell you a little bit about what higher order networks are, and they're a way to represent these observed walks. So any kind of observed walk data, ships through ports, cargo through ports, passengers through airports, people through public transit, all of these kinds of things. Anything that can be modeled as a discrete thing moving through a network. How do we turn that into network data that takes into account these higher order patterns because the data is sequential? So let's look at a toy example where we have this data set S, and it has 235 walks, all of length 2. And we can count some things from this data set. So we can count how many times each edge occurs. So we can say AX occurred 30 times, BX occurred 205 times, and so on. And we can also count patterns that are longer. So in this case, 2 edge walks. And so maybe AXC happened 30 times, but AXD never happened at all. And so what can we then do with these histograms? Well, the first thing we've already done in the first example, we can take the histograms that we've counted and turn them into a weighted and directed network. And then we can think of this network as a model for how things can move through the system. And so we can try to simulate random walks from this model of the system. And the random walks that we generate from this network will have proportional edge frequencies. So we'll still, as long as we put the right proportion of walkers on both of these nodes, we'll get a histogram that looks something like this. And that's great. However, it can't give us the same walk counts that we saw in the real data, because this model is too simple. And the reason is that in the real data, we saw AXC occurred 30 times. So every time a walker took the edge AX, it then took the edge XC. But in this model, there's no memory. So when a walker is sitting at node X, it doesn't remember whether it came from node A or node B. And so it independently chooses between C and D with probability proportional to these weights. And so if we just run random walk simulations, we're going to get a bunch of AXD walks. And so we can't reproduce these higher order frequencies. And so we need a different model. We need to add some complexity that can actually account for higher order patterns in the data that we're observing. So we could think of order on at least 3 orders here. So a 0th order model would be like a bag of nodes. So I'm just pulling out a node regardless of whether it's connected to any other nodes. There's no structure. So I could get walks that would look like B, B, D, C, for example, because there's no network structure to respect here. And then I can go to the 1st order, which is what we've already looked at. And now we have a network structure, but like I was saying, there's no memory. So this is sometimes called a Markovian random walk on this 1st order structure. And then where we're headed is to higher order models. So here I have a 2nd order model. It still has a network structure, so it's still a directed and weighted network, but now it incorporates 1 step of memory. And this is called a DeBruijn graph. And so we can take any set of observed walks and we can construct a DeBruijn graph from them. And in a DeBruijn graph, the nodes, so in a DeBruijn graph, kth-order DeBruijn graph, the nodes represent walks of length k-1. So if we think of the 1st order graph, k would be 1. So this is a walk of length 0, which is just a node. In the 2nd order graph, we have walks of length 2. And 2 minus 1 being 1. And so edges become nodes. And then an edge in the kth order graph represents a walk of length k. So this edge from AX to XC represents the walk AXC. And we can put the same weight we had in our histogram earlier here. And now a Markovian random walk on this 2nd order model is in fact accounting for the 2nd order probabilities. So now if I start random walkers from these 2 nodes, then I will recover this these walk probabilities, because for example, there's no possibility of going from AX to XD, which was the problem with using the 1st order model before. So these I've just introduced generally as ways to model, represent this kind of observed walk data, but we're also going to use them to count and understand sequential motifs. So back to the motifs. An observation is that every walk or sequence on k edges corresponds to a motif also of length k edges. So for example, here we have a cycle that goes from Boston to JFK to Chicago and back to Boston. And this is represented by a motif that starts at any node, but let's say it starts here and goes to the other 2 nodes and then returns to the same node again. And so we can go from the walk space into the motif space just by assigning each node to a unique identifier and then replacing the node in the walk with that identifier in every place, and doing that for every walk in the data set. And then we have the count of all of the different motifs. So for example, we can start with Boston. We can label it A. We can label JFK B. And then we go back to Boston again, and we're back at the same node. We just label it A again because it's already labeled, and the same going to JFK again. And so now this sequence or this walk is represented by the motif that goes from A to B to A and back to B again. And if we do this in the same way for every walk, then now we have a count of all of the different kinds of motifs. So a formal definition is that sequential motifs are sequence-ordered multigraphs, which means that the edges have a specific ordering. So there's an integer associated with each edge that represents the order that the edges should be traversed in. And there can be multiple edges between pairs of nodes. So that's the formal definition of a sequential motif. And so a motif has a sequential interpretation if there's an Eulerian trail through the graph representing the motif from at least one node. So for example, and so an Eulerian trail is a walk through the graph, in this case, a multigraph that visits every edge exactly one time. So if we look just at this chain, if we start with this node, then we can get over both edges without having to teleport. And so that's an Eulerian trail. And the same is true, for example, here, where we can go from 1 to 2 to 3. We've touched every edge, so there's an Eulerian trail. But if we look at these motifs on the left side, where there's only a static interpretation, then we can go, if we start at this node, we'll end up stuck here. Same will be stuck here. And so there is no Eulerian trail in these motifs. And so the formal way to tell whether there's a sequential interpretation for any motif structure is whether there's at least one Eulerian trail going through it. Okay, now we know what they are. How do we relate sequential motifs back to DeBruijn graphs? Well, since every walk corresponds to an edge in a DeBruijn graph and vice versa. So if I have a kth-order DeBruijn graph, that every edge there represents a walk of length k, then I can project the edges of the DeBruijn graph into motifs. And so that's what I'm doing here. So I have this cycle again. I split it into 2 nodes, but it represents the same walk. And then I have the same cycle is the motif corresponding to this edge in the DeBruijn graph. So we can count our sequential motifs by projecting the edges of the DeBruijn graph. And for each edge, we project it into its walk, and then we get the motif. And we can also, don't worry too much about the details here, but we can simultaneously construct a DeBruijn graph and count the sequential motifs. And you might be noticing that neither one is necessary for the other. So now we can actually connect why we care about DeBruijn graphs at the same time as we care about sequential motifs. And that's because of this. So counting motifs gives us some intuition for their relative importance. So if we have this 2-edge chain and this backtrack, we might ask a question like, is the 2-edge chain more important than the backtrack? But that's really hard to say in networks because they're very complex topological objects typically. So the question of, is this big, is not answerable without having some kind of null model to compare against. And so that's what we're going to use the DeBruijn graphs for conceptually. So instead of just asking, are these bars bigger than each other, we can define a null model for DeBruijn graphs that allows us to compute random DeBruijn graphs that are based on the same input data. And then we can compare the counts of the motifs in the null model with the actual observations that we saw. And so in this example, we asked, is this bar big? Is this number of motifs big? If the null model says in random data, there's not very many, then we might say, yeah, that's actually surprising that we're seeing this many observations of chains. But maybe in this case, we don't think so as much because the null model ended up with about the same amount of backtracks as the real data. Yeah. So it's just predefined. So you choose, like, I'm interested, in this case, I'm interested in motifs of length 2 edges. And so I would look at the second order DeBruijn graph. But yeah, that's also one of the future things is like looking at multiple orders at the same time. Didn't exactly do it that way yet. Yeah. Yeah, that's exactly where we're going. So yeah, so in the typically network scientists are going to use a configuration model. So that's what they did in the seminal work back in 2002. So they had their real network and they were looking at how important is this feed forward loop in the red, and they saw it a lot in their real network. And then they used some kind of degree preserving randomization, so a configuration model where every node ends up still with the same degree, but they rewire the edges randomly. And as you can see, there's many fewer of the motif they're interested in the null models. And so that allows them to say there's something about the way the system is organized that's not just random chance. And so we're doing something very similar, but there's a bit of complication with DeBruijn graphs. So we still are going to design null models that are randomizations of kth-order DeBruijn graphs. So we're going to talk about DeBruijn graph ensembles. But stub matching, which is the strategy I think they took here, where you just rewire the edges, doesn't really work in DeBruijn graphs because not every node can connect to every other node. So you have to have this overlap. The last k-1 nodes in first order nodes in the source have to match the first k-1 nodes in the target. And so if you don't have that, then you can't rewire. And so you can't just use standard configuration models on the DeBruijn graphs. We have to do something a little bit different. And so now we'll go through them. I'm going to talk about 3, and I'm going to use this figure to help. So here we have a set of input walks. So this is our input data. We have the first order graph that's constructed just from the walks. It's not weighted or anything. And then here we have the second order DeBruijn graph. And the black edges represent the observed graph. So these are the edges that we actually observed in the data. So this one represents U1, U2, back to U1. And we actually did observe that in this data set. And then the red nodes and edges are things that we didn't observe, but they're possible given the first order graph. So there are some things like, for example, we didn't observe U0 to U1 to U2, which is what this edge here represents. But U0, U1, U2 is possible in the first order graph. And so we call the combination of the black and red edges and nodes is the complete DeBruijn graph. And we call it G super K sub C. And just the black edges and nodes we call the observed DeBruijn graph. And so these two of our null models are going to be based on the observed and the complete DeBruijn graph. And then I have the same thing here just for the third order. In this case, there's in the observed DeBruijn graph, there's actually 3 different components. And then in the complete DeBruijn graph, you have something that I think is at least weakly connected. So the structures can be quite different when you add all of the possible things from the first order graph. And then on the bottom, I just have the types of motifs that we can get from these 2 structures. So the backtrack, the chain, the other chain, cycle, and so on. Okay, so the first of the 3 null models is going to be to take the complete DeBruijn graph and sample uniformly from all of its edges. And it turns out that corresponds exactly to sampling uniformly from all possible walks through the first order graph of length k. So if k is 2, then it's all possible walks of length 2 through the first order graph. And so the idea there is that the only thing we're preserving is the first order structure and the length. We're not preserving the edge weights at all. We're pretending that they're uniform or making them uniform in the null model. And just as a side note, this is different than simulating random walks. So if we look at this little tree, if I simulated random walks on this, then for example, the probability of SUV would be 1/2, because it's 1/2 chance to go to U from S, and then deterministic to go from U to V, so it would be 1/2. But what we're doing in uniform walk sampling is taking all of the possible walks and then sampling uniformly from them. So here the probability would be 1/6. So they're related but different processes, and there's not the same kind of degree bias in the uniform walk sampling as there is in a random walk. Okay, so the second null model is the same, except instead of sampling from the complete DeBruijn graph, we sample from the observed DeBruijn graph. So instead of sampling from all of the edges, including the red, we sample only from the black edges. And so here, now we're constraining the null model to things we actually saw, but we're fully randomizing the weight of the edges. So we're just uniformly sampling from all of the edges. So that's the second one. And then the third is called HYPA, and I forgot the citation. This is from a previous paper we did about hypergeometric higher order path anomaly detection, which is a mouthful. It is in SciEM Data Mining 2020. And the idea here is that we're sampling, again, from all the observed edges, so just from the black edges, but now instead of uniform probability, the probability is based on a k-minus first order model. So if we're looking at the second order model, then the probability or the frequency that we'll get from sampling a network from this ensemble, the frequency of any edge will be the frequency you would expect in a first order random walk of length k over, or many first order random walks of length k. And this is actually a soft configuration model for kth order DeBruijn graphs. So soft because it preserves the expected strength of the higher order nodes. So it preserves expected weighted degree, whereas we would call a configuration model hard if it preserves the degree exactly. And so this one, I don't think I'll talk as much about in the results, but it's another thing that we tried, and it's based on some previous work. Yeah.
For example, in second order DeBruijn graph,
Mm-hmm.
you go like U1 and U1, U4, you go to U2, U4, because they require the last node to be the same as the starting node.
So it requires the last k-1. So yes, in this case, the last node needs to be the same as the starting node. Yeah, exactly. Yep. Any other questions? So we can think about this as more random to less random in scare quotes, because it's not very precise. But in the complete DeBruijn graph, the only thing we're fixing is the first order structure and what walks are possible through that. Everything else is uniform. In the observed DeBruijn graph, we constrain by taking only the paths that we've observed before. And then in HYPA, we also look at paths or walks that we've observed before, and we also preserve the probability or the model up to k-minus first order when we choose the weights of the edges rather than choosing them uniformly. Okay, so now we talked about null models and counting, and so we can look at some data. So we have two data sets. The first is flight itinerary data. So exactly as I described before, it's passengers moving through the domestic US airport to airport network. Here's the path length distribution or the walk length distribution. There are some very small number of surprisingly long walks. I don't know who's taking a flight with 15 airports, but apparently someone has bought that ticket according to the survey that they do. But most are, under 5 or 6 airports, which even this is surprising how many people are taking six airplane trips. And then the second data set is the Wikipedia game. So this is a game where people are placed on a random page on Wikipedia, and they're given a target, and they have to use the hyperlinks to find the target page. We're looking here at all the pages, all the games that were finished successfully. So they're mostly relatively short, like a few hops. We think this one was probably some kind of robot, because otherwise it's a person with a lot of patience to go that many steps before they finally find it. Yeah, so these are the two data sets we're going to look at. And these are the figures that we'll go through. So on the sides here, we have the motifs. So each row corresponds to the same motif. These are the 2-edge motifs. So we have the backtrack and the cycle. And then these are the 3-edge. So this is a chain, not a cycle. And then we have the chain here. We have the actual cycle here, and so on. And then each of the bars is, so the first bar, the gray bar, is the actual observed amount. And these are in thousands on the axis. So that's the total amount we actually observed in the data for the flights and for Wikipedia. The two in the orange are the complete DeBruijn graph and the observed DeBruijn graph. And then we have hypa in this kind of green. And then I won't talk about these, but these are just random walk and weighted random walk. And they're more for comparison than anything else. So to start with, we note that chains are very common in both data sets, which makes some sense. To get anywhere in a network, you do have to go forward, and so you have to move across different nodes. And so generally they're the most prevalent across the data sets that we've looked at. Backtracks are also overrepresented in both data sets. So by overrepresented, I mean that the observed value is much larger than the random average value in any of the null models. So these, I think, are averaged over like 10 random samples. So basically, we sample the same number of walks using each null model as was in the observed data, and then we count how many of each motif that we see. And so backtracks being overrepresented makes total sense in the flights because people prefer round trips. And so that's what a backtrack corresponds to in the flight data. And in Wikipedia, it corresponds to hitting the back button in the game, which also seems reasonable. Probably if you're searching for something, you end up having to go back a lot. So you went to one page, it didn't have a link that looked better than the links that were on the previous page, and so you go back. But there is a difference between these two. So in the Wikipedia data, in the observed DeBruijn graph ensemble, so where we're sampling from the observed links, we see that the counts are actually quite similar to what we saw in the observed data. And so this now connects to the distribution of edge weights. So when we have that the uniform sampling is giving us the same count of motifs as what we saw in the real data, the implication of that is that in the real data, the edge weights are very small, pushed across a lot of different edges. Because otherwise, when we sampled uniformly, we would see a big difference because the edges that were had heavy weights would only be sampled a small number of times. And so indeed, that's what we see. So especially for the chains and backtracks appear a very small number of times in the Wikipedia data, which also kind of makes sense process-wise. Probably the same page backtrack combinations are not coming up for different source target pairs and different people searching. The Wikipedia network is very big and sparse. There's lots of options for where to go and get stuck and have to go back. So it kind of makes sense that there would be fewer, that every backtrack appears just once or twice or some small number of times. But this isn't the case in the flights data. So the number of sampled backtracks from the observed DeBruijn graph doesn't match what we saw in the real data. And so that implies that there's a heavier tail on the backtracks for the flights. And this, again, makes sense because if backtracks are round trips, people are not randomly taking, like there's not round trips where only one person ever took them. It's likely that these round trips are representing, New York to Washington, D.C. and people taking them over and over again. So we expect to see some with very high edge weights and others with relatively low edge weights. So this heavy tail makes some sense. Okay, and finally, to get back to something I said way at the beginning, we see the triangles are overrepresented in the flights. And now this is relevant to the first example. So here I'm comparing the sequential motif analysis with a static motif analysis. So here I have the count of observed sequential motifs, the average in one of the null models. I think it's the complete DeBruijn graph null model. And we see that we observed more motifs more cycle motifs than we saw in the random. So we would say this directed triangle is overrepresented in the sequential case. But if we look in the static case, the observed is smaller than in, I think this is just a configuration model, and counting the same, counting triangles again, now it looks like triangles are underrepresented. So not only is it the case that these directed triangles, which are like a direct flight in one way and a layover in the other way, or just a two-city trip, they could be a lot of different things. Not only are they overrepresented, but if you looked in the static, if you use the static techniques, you might see the opposite. So in this case, with the gtries algorithm, we did see the opposite, that there was, it looks like this motif is underrepresented rather than overrepresented in the data. Okay, so some things for future work. The hyper-null model that I didn't talk about as much today can be really flexible. It can encode all sorts of spatial and semantic relationships between higher order nodes. So that's something that we might look at in the future. Nested motifs, which kind of gets at choosing the order, like Shazia asked before. Higher order motifs have lower order motifs as substructures. And so it's a question of whether there being an overrepresentation of a higher or lower order motif implies something about the other, vice versa. There's also, we can use these sequential motifs for embeddings, and use those for prediction or other things that we do with the embeddings. And also, as I said earlier, connecting sequential motifs with other work on discrete random processes, like the work of Schwartz and Porter on process motifs. And that's it. Thank you for listening.